Our final speaker, we're very privileged to have Professor Li Zheng with us today. He's a professor and executive VP of the Institute of Climate Change at Tsinghua University. For everyone out there, Tsinghua University is the Oxford of China, and for our Cambridge colleagues out there, that means they're the best university in China. And we've got Professor Li Zheng, who is the president of the Global Alliance of Universities on Climate, to speak to us today on getting down into the deep dive of what this means for China, the carbon neutrality and the progress they're making. Thank you, Professor Li.
Share screen.
Okay.
So thank you, Matthew. So I come from Tsinghua University. And before I start, I would like to say my appreciations to our Oxford colleagues. Oxford is a member university of Global University Alliance of Global Alliance of Universities on Climate. So I play as a Secretary General of the Alliance. So first I appreciate Oxford contribute to this great event to the GOC activity. Secondly, as you have just heard, so I appreciate that our colleagues from Oxford paid a lot of attention to China energy system, not only the global one, but also Chinese energy system. So I appreciate your effort. So now I would like to share something our study on the decarbonization pathways for China and is power sectors. So as you know that China has announced, so our President Xi has announced China will reach carbon peaking before 2030 and reach carbon neutrality before 2060. So that's a big effort. So in my understanding, that needs radical transformation of the whole society, including energy system. And I did not prepare much about the whole energy system, but I would say that to conduct that transformation, energy system is the most critical. So China's energy system is now composes of 84% of fossil energy and about 15.8% of non-fossil energy. So to reach carbon neutrality, I think the share should be reversed. So we need to establish an energy system with 85%, more than 80% of consumption from non-fossil energy. So I think that's just our future. So to realize that future, electricity power sector is very important. And normally people think that power sector should go ahead to support the transformation of energy system. To support the energy system transition and also the societal one. So for this purpose, my group made a study to look forward up to the year 2050 to look at how can we conduct the transformation of a power sector. And so we developed our own model called LOM-LOG. So that's so this model use the superstructure modeling technique, and it is the optimization model to pursue the least cost for whole energy transformation by inserting different technologies, especially the renewables. Our two colleagues have mentioned. So and the characteristics of this model is that we are starting the long-term transition of the power sector, the technology transformations. However, we also while this evolution of the whole of the time, we considered the power balance for short term. So that means so we believe that this kind of approach can get more accurate estimation about the future technology demand. And so basically we are for this study, our planning horizon is from 2018 to 2050, and we considered most applied power technologies, so that 14 plus 1. I will mention that. So that means from the fossil energy to renewable to wind to solar, and also we considered CCS that can be retrofit. The coal power plant can be retrofit to with CCS. And as you know, China is a big country. It's very big. So if we treat China as a lumped node without considering the power transmission, then we think that the estimation may be not accurate. So we for this reason we divided China into 17. According to the structure of power grid, we divided China into 17 regions. That means each region can be connected with transmission lines. And so in this way, that means for one region, the power it needs can be not only produced by itself. If it's cheaper, it can be transmitted from other areas with plentiful renewable resources. So this is roughly the concept of the model. So as I mentioned that we divided the whole China into 17 regions, and we considered the existing power transmission lines, and also we considered, because we are talking about 30 years later, so we have considered all the planned transmission lines. And then after 2030, there's no plan. Then our model will optimize. Each two regions can be connected in our modeling. In our model, then the optimization will select which transmission lines could be built that can save the cost. And as I mentioned, that to be accurate, we can we divided 1 year into 4 seasons. That means resources are different. So in winter, winds are higher, and then for each season, we select a typical day that divided into 24 hours. So that means we use 96 time slots that simulates the whole year power balance diagonally, hour by hour, and then at the same time, the power demand increases along the year. So the optimization, the time horizon is 30 years. So we simulate the under the constraint of power supply balance, then to sum up the cost, sum up the cost for each technology in each region. Then we do optimization, find we do the optimization in a holistic way to find long-term planning plan. And then for technologies, we considered most existing power technologies like coal power, like natural gas power, hydropower, nuclear power, wind onshore, wind offshore, PV, concentrated and distributed, etc. We also considered the biomass power generation, and then for the fossil energy and for the biomass burning power plant, we considered the CCS retrofit. So that means for each time node, we make for each technology we made 4 choices. Whether to build, newly built, that's one choice. The second is retrofit with CCS. The third is to decommission the existing capacity before design life. And then fourth is to decommission the facility when it is design life meet. So for each time node, we considered, for each technology, we consider 4 choices. And then the superstructure technical can accommodate simultaneously all the potential cost that can be used for optimization. And as I discussed with Matthew this morning, so we consider the technology efficiency improvement along with time horizon, also the cost change, and to make the modeling more practical. We also considered for coal power plant in the future, it may to help the renewable power operation. The coal power plant may run in off design load, so the efficiency loss are also considered in our modeling. And under storage is described in that if so that's under storage technologies are considered also in our modeling, but they are competing. So the major principle is that all the technologies in our model is competing each other, that to reach minimum cost for the whole country. So our cost includes not only the operation cost for fuel, but also the investment for construction, and the investment for transmission, and therefore also we consider the cost for CCS capture, but we did not consider the transportation cost. So this made the model quite powerful. So we can see that we can describe along in 30 years time horizon to meet the local power demand with different technologies. So that means it is a mixture of technologies, and we can also describe how to transmit power along regions, and we can also check whether the existing power transmission is effective or not. And we can check, because we have diagonal modeling, so we can check the power balance hour by hour. And for policy making, we can check for a 30 years horizon how the CO2 emissions behavior of each region. That will help to give a better policy. So this ends my methodology introduction. Then by using our model, we started for the power sector evolution for up to the year 2030. We considered four scenarios. The first one is business as usual. That means before this time point, China has our previous NDC. So along that speed for renewable under development, so that we call it business as usual. Then the second scenario is enhanced NDC scenario. That means to increase our target for 2030 from 20% for non-fossil energy to 25%, and then keep this speed after 2030. Then the third scenario is a two degree scenario. That means we need to meet the IPCC Paris Agreement 2 degree target, and the fourth is 1.5. So I think I need to. So I think now I introduce some result. So our finding is that according to the previous speed for non-fossil energy development, and also for increased for enhanced target, and keep that after 2030. Both policy scenario, business BAU scenario, and the enhanced scenario cannot meet the 2 degree target. It is here. This means that after speed up before 2030, we should further accelerate the development of renewables to meet the 2 degree target. And then for the 2 degree target, we have different choices. That means late response, medium response, and immediate response. So you will see that you can look at the carbon emission trajectory. So to act immediately, you can have a more relaxed pathway. But if we act late, that means to increase. We act late, then the trajectory will be very abrupt. So that means a lot of fossil energy power plant will be decommissioned earlier. That could cause some problem with this unstable problem with society. And then for 1.5 degree target, that will be very difficult. That will be very difficult. That's very abrupt. Later I will show the result. So to reach the trajectories I have just mentioned, business as usual enhanced and 2 degree and 1.5 degree. So here just give some impression about the technology mix for the future. So roughly speaking, it is the installed capacity for the first two scenario and the third and the fourth are approximately 4,500 gigawatt, 5,500 gigawatt, and 6,500 gigawatt. That means 2.5 times, 3 times more installed capacity than it is right now. And if you look at the contents, so although the carbon emission trajectories are quite different, as I have showed, but for all the scenarios, non-fossil energy will be dominant. So the difference for remain fossil energy varies a little bit, not very little. The absolute amount are not small, are not large, but the carbon emission trajectory will be quite totally different. And I would say that BECS, BCCS, and the CCS is adjuster. So with more carbon capture, as you mentioned, then you can leave a little bit more fossil energy. But if you don't take this technology, then if you want to meet 2 degree target or even carbon neutrality target by 20 for 1.5 degree scenario, then you need only non-fossil energy. So that's the difference. And for the power generation amount, you will see that more than 90% power should be generated from non-fossil energy. And among them, about 55 to 60% power will be from intermittent renewable wind and solar. So to stabilize the power grid is a big target. That means we need a lot of I would say that. So here, just some comparison. Compared to the business as usual for 2 degree scenario and the 1.5 degree target. So we need to develop more non-fossil energy, especially wind and the solar. At the same time, we also need to apply CCS. And the long distance, long distance transmission requirement also increases when we have a higher target for carbon control. And CCS is certainly needed to minimize the cost. So our estimation is that it is run by 2050. The requirement for CCS could be between 600 million to 1,000 million tons per year. So that's quite big. But because China's power fleet is still dominated by coal power. So its average age is around 12 years old. So the stranded asset, the value, the loss for stranded asset is a big thing. You can see that for different scenarios. So more coal power should be decommissioned. So the higher the carbon target, then the more stranded asset. So we have to deal with that carefully. And you can see that for 1.5 degree scenario, the cost, the stranded assets loss is big. But for 2 degree scenario, if we act earlier, then the loss could be reduced. And we also need a lot of investment. So in the morning you talked about the cost. So maybe in the long term, the power price could be reduced, but in between, in the process, because investment, you need a lot of investment. So we expect that the power price could increase for some time. So roughly speaking, compared to the current level of investment, to decarbonize the power sector, we need to increase our investment from 1.3 to 1.9 times per year, lasting for 30 years. So that's quite big. So we estimate for whole energy transition, China needs to invest about 100 to 140 trillion yuan for whole energy system transition. And among them, about half are for power sector. And this is roughly what I have finished. So the last technology is about we are thinking how to improve the behavior of coal power. So one solution is co-firing with coal with biomass that do carbon capture. That can help to improve the carbon performance of coal power very much. So this is roughly what I said, and for the time limit, I don't talk that much. I think finally, the policy recommendation is more. I think you can imagine that. So firmly develop renewable energies. I think that's the right way. At the same time, pay to do technology innovation for CCS, energy storage, high voltage transmission, and then finally we should also to ensure investment. Without investment, without green finance, I think the transmission it cannot be realized. So this is roughly what I report to the audience. Thank you for your attention.
Thank you, Professor Li. We've got time for one question. Is there any questions on the chat or any questions in the room? Myles, Professor Li, would you be able to answer a question from Myles?
Thank you. Am I audible? All right. Yeah, I am audible. I just wanted to ask. Thank you very much for that, Professor Li. That was really interesting to hear. How does your model is a power sector model? Have you plans to extend? I mean, I'm thinking about the industrial emissions and other emissions that will also need to be part of this decarbonization pathway. Is your model integrated in with other models that would allow you to model the full emission pathways, or how is that done in China? Or
it works. Okay. So my organization organized overall hierarchy strategy study for China, including from economic development, from urbanization, from industry sectors, from agriculture, as all greenhouse related sectors. So we organize a team to work separately, and then we do integration exercises. So in this sense, so the power model is one of the bottom models.
Yeah.
So in this sense, we didn't have an integrated model yet. All the people use their own model, and then we do a lot of work to integrate them together to form a whole picture for China that help the strategy making. But at the same time, in my group, we are doing two things. One is we are quite mature with this power sector. We developed that for a long time. And at the same time, we also developed some system model, including all the power, all the energy supply system, plus the consumer sectors. But I didn't show that.
Yeah, that'll be very interesting, because I think a lot of as we really grind down emissions, a lot of the interesting interactions will become between, say, heavy industry and the power sector. I'm thinking about, you were talking about load balancing. To what extent will you be able to use big industrial consumers to manage the load? And so that's interesting. It's good to hear you're working on those fully integrated
we are
models.
working on that. That's exactly our target. So my team is working on the 2060 carbon neutrality pathways. So
yes.
we use more integrate, we use more modeling work, and at the same time, I'm lucky to meet you too. Yeah, so I would like to keep contact, and maybe we can have more communications and even collaborations.
Absolutely. Well, one thing, as Matt
Great.
knows, one thing I'm very interested in is actually modeling. If you actually had a carbon takeback obligation, just hypothetically, what would actually happen in a big?
Sorry, what's the question?
If you actually, it's just this is not a question. This is a proposal. Yeah. But it would, I think, be very interesting if we had an integrated model of both industry and power in China. What would happen if you imposed a carbon takeback obligation on that? How would it map through? What would happen to prices? What we did in our study was a very idealized model of the whole world. But in the end, policies don't get implemented on the whole world. They get implemented in countries, in jurisdictions. And so it would be just as an academic exercise, it would be very interesting to explore that. And I hope you can consider this, and maybe find a smart graduate student who might like to come and visit us in Oxford to pursue that.
Okay, that's great. That's a deal. But roughly, I can try to answer your question. So I think for China, also our commitment is quite clear. So we will peak our energy-related carbon emission, carbon dioxide emission before 2030.
Yes.
So it is not by 2030, it's before.
Yeah.
And so now we have a very sound, concrete policies to support such kind of target. We have a target.
Yes.
We have set up a strategy under our target. By 20, I think if you look at our new document, you can see that the document name and the working guidance have set up 3 time nodes: 2025, 2030, 2060.
Yeah.
So we set up 5 indicators for each time node. So that's target very clear. And then we have policies, action plans for each industry sector and cross section issues.
Yeah.
So this document are the action plans that support to realize this time target. So I would say that China has a very sound plan, and the whole society has been equipped with the mood to be able to go that way firmly.
And dare I say it, perhaps much better equipped than other societies for this transition that we face. We're reaching 10:30, so we have to vacate the room, I think, at this point.
Yes,
thanks very much, Matt. Thanks for
the
organizing.
team to have their talk.
Thank
Thank you both, Professor Myles Allen, Professor Li Zheng, for your expert advice today and for your time. And thank you for everyone for joining us here today.